Okay, we're off and running PF1, wow, video 5. And I did then this morning, if you look here, I did grade your VI labs in your Unix Lab 3 directory. I haven't posted the grades on Blackboard just yet. And for the record, I'll say that will sometimes, perhaps even frequently, lag a little bit behind. But, you know, we're supposed to give you guys your feedback on your labs and tests and everything else in a timely manner, one way or the other. And anyway, you'll find your grade at the bottom of your README file. Of course, at this point, you know several ways that you can look at that. Go to your Unix Lab 3 directory and you can cat it, or you can more it, or now you can VI it then also. So you can check that, and I'll get the grades posted soon, I guess, on Blackboard then. And you guys did a good job there. Appreciated the information you gave me then on yourselves and where you've been and where you're headed and those kind of things, you know, and some interesting stories and a couple good jokes. So I did enjoy reading your README files then this morning. So thanks for taking the time to do that. And so with that then, we've wrapped up our introduction to the development environment. And so now we're going to start talking about programming from here on out then. And we're going to be using the Java programming language. And it's a really, really, really good first programming language. It's very popular, has been. It's been in the top 4 programming languages. And to be clear, there are tens of thousands of programming languages. You know, there's many of them that you hear about, more than others, certainly so. But anyway, Java has been in and out of #1, and it's always been in the top 3 or 4 for the last 25 years, something like that. So a very popular programming language. But it's kind of a really good one to teach a first course in computer programming. And also then it shares the syntax with some other very powerful programming languages. Also they're very popular then. So anyway, that's the one that we've picked. But so we're going to give you a little bit of Java history then today also. And we're going to back up a step before that then even just talk about some programming history. You know, if you're going to study computer science, it's nice to know something, I guess, about computers and computer programming history and those kind of things, you know. So let's get to our notes. All right. And zap down to the bottom here. Guess we can make that a little smaller now. Yeah. Okay. And video 5. All right, programming history. Well, I guess the good news is, in terms of history, you don't have to go back as far as we might in some other fields of study. You know, we think about different majors within the general category of engineering. Some of them are certainly older than others. You know, if we're studying civil engineering, how far might back we need to go in terms of civil engineering? You know, roads and bridges and, you know, aqueducts and those kind of things, you know. Oh, I know, at least back to the Roman Empire, you know, that goes back a good long time, you know, or perhaps before, you know. I'm assuming there was some engineering interest and skill set and so on that it took to build the pyramids and everything, you know. It's a good long time. And other areas of engineering, electrical engineering, that's going to be not so old, certainly so. You know, good heavens, with the light bulb and so on just having been invented at the end of the 1800s, you know, whatever that is, 150 years old or something like that now at this point. That's a newer area of study. So what about computer history? Now, you know, there were some kind of mechanical calculating machines that were invented in the late 1800s, early 1900s. Oh, the most famous one, there was a guy named Charles Babbage. Kind of a funny name. And anyway, old Babbage, he created a machine with a big crank, and it could do addition and subtraction, you know, kind of an adding machine kind of a thing. And it was called the Babbage engine. And anyway, that was from the late 1800s. But what about, you know, electronic computers? How long have they been around? I will just ask you guys, just for grins, I guess, you know. Y'all have any guesses? That's a very good guess. That's right. Maybe just a little before that, you know, and that's a very good number. That's when they kind of started to sort of to become a little bit more mainstream. Certainly not in terms of home computers, but at least starting to sneak into, you know, good-sized businesses and, of course, government and universities and those kind of things. So the 50s is good. A lot of very popular programming languages were created in the 50s. We can go back, maybe a decade or so, a little bit before that even then. You might remember that, hey, during World War II, also then computers played a role. What important tasks did computers help with? Probably many, but I'm going to say that the most notable task that the computers helped us with in World War II might have been code breaking. Very, very good. That's exactly right. So, you know, we had experts, you know, in the U.S. and England and so on. Of course, we're allies, you know, and so teams of people that were working on breaking the codes of Japan and Germany and whatnot with a pretty good success, in fact, and that certainly gave us some help in some key battles and so on, you know. So yeah, those were electronic computers, and those are pretty early on, you know. So yeah, I would say for the most part, I might credit the 40s as far as the earliest practical use of electronic computers, and it didn't take very long then after the war that also then they started moving their way into businesses and so on, and then more government agencies and so on. And then, as Michaela said, that's exactly right. So, you know, I guess just to hit the high points of early programming languages, let's just mention that there's said to be 3 generations, if you will, of programming languages. So, computer programming language generation. All right, computer programming, language generations. All right. So there were 3 of those. All right. Now we'll do it this way here. Okay. So the first generation of programming languages was machine code. And in machine code, everything was numbers. Everything was numbers. The data you're working on was obviously numbers. You know, of course, those earliest computers, well, they weren't, you know, selling I don't know, selling clothes online on the internet or whatever else like that. Of course, you know, they're just doing number crunching. So, you know, they were doing, you know, engineering applications and so on. And so number crunching. So the data was numbers. And then also the code itself was numbers. Everything was numbers. So if you're working on a program, you're just literally looking at a sea of numbers. And it'd be pretty tough to read, and tough to write, and even tougher to read, and so on. And actually, I can save us some typing on here. We can go and mention, tell you what, let me see what I've got in my little cheat sheet. And at the same time, I'm going to show you guys how to copy and paste then within PuTTY, you know, to and from Microsoft, for instance. So I'm going to come over here and see what I have. I remember I put something together, and I just looked at it again this morning briefly, so we'll see how it's formatted. So it will be the case now and then, and I'll mention this now and later also then, that later on, starting our next class period, we're going to be writing programs every day for the rest of the semester. And if it is the case that you get behind or there's a problem in your program and you can't get it fixed and it's very aggravating or whatever, feel free to yell at me and I will copy my version of the program I'm working on right then. I'll copy it to a common location. You can copy it to your directory and boom, you're caught up. You know, you'll just overwrite the one you had that had some unknown bug or whatever. I know that even that's probably aggravating, but it would bring you up to speed. So anyway, in all of my courses, PF1, 2, and 3, I have a little directory where I can copy things that are specific to that course. And there's not much in there now, but anyway, for you guys, /u/temp/PF1. And right now there's just a couple of things. There's this Java API. We'll get to it later. I left that there from last semester. We'll get there eventually. But for right now, well, it's a big long file name, Programming Language Generations. So you guys, you don't even have to go to that directory as far as that goes. You can kind of be wherever. But if you type cat/u/temp, notice there's no E in temp, /PF1. And check this out, I'm going to type PRO, and man, that's a long file name to type. So a nice thing about Bash, it will do file name expansion. It will go and complete this file name here, assuming there's no other file names that start with PRO, and I can just type a tab. So check this out, when I hit a tab, poof, and it goes ahead and completes that for me there to save me some typing. Now I'm just going to cat it because it's not too big. I don't remember, maybe it's a little over a screen. Yeah, you know, there we go. So there we go. There's the contents of this file, Programming Language Generation. So if you guys do the same thing that I just did, and you have it on your screen, now highlight it. All right, so there you go. Take the old mouse and highlight it. And anyway, the nice thing is, in PuTTY, when you highlight some text, it is automatically copied into your Windows clipboard. It's in your clipboard. Now you notice you don't have to type a Control-C or anything, you know, or right-click and copy or anything. When you highlight something in PuTTY, it goes into your Windows clipboard. And now I can come over here and maybe I'll just get rid of my one and just paste in what I just copied, and we'll see what we've got there. All right, so let's scroll on up here. And hey, this looks pretty good. Programming Language Generation. So we're going to put a big number 1 here. Or just go up above it. 1 is going to be machine code. That's how we would refer to that. All right, machine code. And again, everything is numbers. Everything. both code and data. In other words, you know, the program itself in its compiled form and the data that it's working on is numbers. And that would be kind of difficult. So here's an example then, a teeny tiny, ridiculously simple example of a machine code program. And anyway, I kept it real short, just ridiculously short, you know, because, well, one, making it bigger is not going to be, you know, any better necessarily. You see, it's just a bunch of confusing numbers, you know. And also for the poor students that are writing things down, you know, then of course, if I actually copied and pasted in some actual machine code program, good heavens, you'd be scribbling down for the rest of the day. So don't feel at all obligated to make this set of numbers just right, you know, but it's just a sequence of numbers. A piece of trivia here, I guess. Actually, in PF2, as a lab that we're going to spend over a month on, we're going to learn how to write programs in, well, the next generation of programming languages we're going to get to in just a second down here called assembly code or assembly language. And we're going to write an interpreter and a runtime environment, do all kinds of things. So we're going to learn a lot about assembly code and also about machine code in PF2. But for right now, you know, all you really need to remember is, okay, the very first generation of programming languages, those poor people, they wrote programs in machine code and everything was numbers. And again, you can just imagine looking at a sea of numbers here. Good grief, that's going to be pretty tough sledding, you know. You'd want no distractions going on while you're studying that stuff. All right, so down here for our second generation then, so those earlier programmers, they recognize, good grief, this is just tough, this is horrible. How about we write a program that would allow us to use some words that are more meaningful then, and that would then convert a program written with these words back into into numbers and so on, just to simplify things. So they wrote some software that would allow them to then step up to the second generation programming language, number 2 here, which is assembly code. Assembly or assembler, you'll hear both of those terms. All right. Now this would be a mixture, if you will, of words and numbers. Which is better, because, you know, we as humans, of course, are kind of better at dealing with words than we are with numbers. You know, kind of think about your contact list on your phone or whatever else. Why do you have that? Because, well, you have a better job remembering you have an easier job. You do better at remembering your friends and family and associates' names instead of their phone numbers, you know, so we can remember their names, and then we're going to map those names into numbers. That's kind of what this assembler does. This assembler, it's a piece of software, allows us to write a program, well, that looks actually like all of this here that's highlighted. We can put some blank space in here. We can put some comments that are just notes to ourselves in here to kind of explain what's going on. And then here's the actual code. And anyway, hey, we've got some words in here. We're reading some things from the user. We're loading registers. We're performing addition. We're writing something back out to the user. So these words catch our attention and they're easier to read. And anyway, the interesting thing is this machine code up here is the machine code that would be generated from this assembly code using the assembler program, which you guys are going to write next semester in PF2. So you're going to learn a lot about assembly code and machine code. It'll all be more real to you then. But for now, just kind of remember the buzzwords. UG, machine code, everything's numbers. Assembly code, hey, it's an improvement. It's an improvement. Now we have these words and so on, and it's a lot easier to read, you know. But even that is pretty tough sledding. And gosh, guaranteed all the folks that were doing all that programming back in the 40s and 50s and early on, at least in the 50s, machine code and then assembly code is what they dealt with. But pretty quick they decided we needed an improvement even on this. So more software was written. Again, assembly code is thanks to some software. Ultimately, it is the machine code. And this is worthy of mention here, I guess. In fact, yeah, let's put that as a little note somewhere up here, is that it is the machine code that executes on the computer hardware. So, in other words, instead of having the computer understand our language, we're going to have to learn the computer's language, and we have to talk in the computer's language itself in machine code form. So the machine code was necessary in those earliest days because we had to talk directly to the computer hardware, speaking their language. But then we wrote some software that would allow the computer to understand some higher level code, you know, once it got interpreted into the machine code that would execute. But anyway, they finally wanted to improve even on this, because here's the bad news about assembly code and machine code. So you go back to the 40s and 50s, and there were a number of computer companies that sold very big, very expensive computers. All right. And, you know, it was kind of a technology race going on then. You know, some of the companies, of course, IBM was a big early one, and Amdahl and Data General, and I'm trying to think of some others, but lots of big companies that sold big, expensive computers. And so a lot of them, they weren't selling them to individual people, of course, or even small businesses, but big business, universities, government, that kind of thing. A small number of companies selling these very expensive computers. And well, the aggravating thing was for the consumer, so you buy a computer from vendor X, and you start writing programs for vendor X's computers, and you're using their machine code and or their assembly code, and that's all perfectly fine. And you get a knock on the door from a sales rep from vendor Y, and they say, hey, we got some good news. We got a new computer, and it's 10 times as fast as the system you're working on now, and it's half the price. That sounds good. But the bad news is it's a different vendor. They have a different hardware architecture, and their machine code is of a different format, and all of the programs that your team has been working on, they're all going to have to be rewritten before they can run on our system. And then all of a sudden this great deal of a more powerful computer for half the price doesn't sound so good, because you've got a huge investment in time and effort of your programmers to develop the assembly code programs for vendor X's machine code or machine architecture. So they decided, you know, we need yet a better series of programming languages. That assembler code is an improvement, certainly so, over machine code, but we need something better yet. So the third generation then, all right. So number 3, the third generation, are the, quote, high level. All right. Code, we'll say. All right, so the high-level code and examples of that. All right, so it was mentioned that, you know, computers started making their way into business, you know, like in the 50s. So what were the earliest high-level languages? What was the earliest high-level language that was used for science and engineering? I wouldn't necessarily expect that you guys to know, but perhaps. And then the interesting thing is, still used a lot today. Okay, that was the 50s. Here we are 75 years later. And this programming language is still in the top 20 of all programming languages in the world. Starts with an F. So here's an examples. F-O-R-T-R-A-N. Fortran. Fortran. Now I typed that in all capital letters because it's an acronym of sorts. So you can go ahead and make a note of this. So some little details I'll mention, but I won't necessarily write. But you can just for your own interest, I guess. Fortran was an acronym, and it stood for Formula Translator, you know. So you've got a formula. Oh, we're trying to calculate projectile motion or whatever, you know. So we have some quadratic formula that we're going to use to calculate the maximum height of the projectile and its distance, you know, for artillery or something to be used in World War II, perhaps. Actually, guys, Fortran was invented just after World War II, so we'll say the Korean War, then maybe that. All right, so Fortran was for science and engineering. And what about business? Now this, I would think you guys would be more likely to have heard of this one, because oh my gosh, is it still huge today. Also certainly probably in the top 10 of programming languages for business. And it runs the world in terms of big banks, big finance, big insurance. So your credit card companies, your investment companies, all that stuff, you know, they all run on big mainframe computers, running programs written in C-O-B-O-L, COBOL. So that was for business. So in those earliest days, these were the earliest high-level programming languages, Fortran and COBOL. And see, the thing about these, well, let me type in some more of these and we'll come back. Fortran, COBOL, oh, how about C and C++ and Java, and, you know, and so we'll say throw Python into this, the popular programming language these days, and on and on and on and on. You know, basically all popular programming languages these days are all third generation programming languages. And I'm going to go and type this in here. The beauty of these high level, when we talk about high level, it means it's not married directly to the hardware. It is independent of the hardware. It is independent of the computer architecture. So you can write the program once, move it to another system, another computer architecture, recompile it, and it works. Okay, so no rewriting the programs from scratch in order to move your program from one computer to another, which you have to do with assembly code or with machine code. So this was huge. It allowed our programs to be portable. We could move them from one computer architecture to another. And yeah, again, interesting thing about COBOL, I guess. Now, again, I've never written a line of COBOL code. That's used exclusively in the field of business. But it is still huge. You get all the big businesses, big insurance companies, the Fortune 500 companies that have headquarters in Manhattan and so on, they are all going to have very expensive, multi-million-dollar computers attended to by an army of administrators and programmers and so on, and all of them running COBOL. In fact, today, the most recent number that I've read is there are over 800 billion lines of COBOL code in production today. In fact, I've read numbers fairly recently say that there are more transactions handled by COBOL every day than there are by Google. All right. It's because every credit card swipe, for instance, is all going to be launched on some COBOL code and be handled by COBOL code. So again, investment companies, big banks, insurance, all that stuff all runs on COBOL. So all right, so there's that. And so that's kind of it, I guess, for our three generations of programming languages. And I would like you to kind of, understand, we started very primitive writing machine code. With some software, we improved upon that, and we wrote assembly code, which was better. But unfortunately, both machine code and assembly code are connected to the computer hardware. They're unique to the computer hardware. But on the other hand, these high-level languages, you can write them once on any system and then move the code to another system, recompile, and it should run there just fine. So that was a big help. Because what we're going to see here when we talk about Java history now is we're going to see some similar concepts. All right, so to be clear, this was, computer programming language generations here. Now we're going to talk specifically about Java. It was mentioned here that it is a third generation programming language, but, it's kind of nice to know when was this language created, what time, by whom, and what purpose was it supposed to solve? There are other programming languages that existed when Java came around, so why the heck did we need Java when we had other languages that could perhaps do similar things? So let's talk about Java history real quick. All right, Java history. So we're going to kind of give you the who, what, where, when, and why, I guess, of Java history. And okay, how about it was created in it started in the mid-90s. All right, we'll say 1995, something like that, approximately. I'll put a little approximate symbol here in front of that. So about the mid-90s. And the father of Java, his name is James Gosling. James Gosling. He was a research fellow, was his title. Hey, put that, some of y'all mentioned, your what you want to do when you grow up in your career, I guess. Hey, put research fellow on you. I want to do this list, Research fellows, they are good idea people. They're good dreamers. They can look at what are the tools that we have now and what problem can we solve that people don't necessarily know that needs to be solved, but when they find out, they're going to beat our doors down trying to buy our product, So they can dream up things, like the first smartphone, for instance, We had computers before then. We even had, cell phones, and there were some phones that also had, calendars and note-taking abilities and those kind of things together, But of course, Steve Jobs is the father, for instance, of the iPhone in around 2007, something like that, when it was released. And anyway, in no time at all, everybody had to have a smartphone, just because of his ideas. Anyway, so of course, Steve Jobs was the president of Apple, and he also was, its founder and kind of the idea person for it. But anyway, there are also people that work for big companies, and they are just good at dreaming up, problems that can be solved that people will beat our doors down to buy our products, So James Gosling was a research fellow. I don't remember if it was James or somebody else. I remember reading about some other researcher, and of course, much of that, especially decades ago here in the 90s, those companies tended to be headquartered in California there on the West Coast. And I remember reading about one, maybe it was Steve Jobs or James Gosling, I don't remember for sure which one. And they said, oh yeah, I get my best ideas when I get in my convertible and I drive up and down Highway 1 on the West Coast, where it just overlooks the Pacific Ocean there, a little winding state highway in California there. It's kind of the westernmost before you fall in the ocean highway there. And so he spent his days thinking up his ideas, driving up and down Highway 1 and on the California coast, So that sounded like a pretty rough job, I guess, then. But anyway, the company he was working for was Sun Microsystems. And Sun Microsystems they've been selling Unix workstations and Unix servers since the, early 80s, something like that. They're still around today, kind of pretty big company. And anyway, so Sun Microsystems. And, what problem was he trying to solve? Well, let's go and type this in. I'll show you a little picture here. So during the mid-90s, boy, oh boy, was there a boom in what I'm going to call consumer electronics. Consumer electronics. Things were popping up all over the place there, and one year to the next, things would get bigger and more powerful, I should say more powerful. Actually, they got smaller physically, and but also cheaper and faster and so on. And I have a little picture here that I put together at one point. Let's go over here, and here we go. All right, consumer electronics, such as, all right, let's see here. Get this moved over and scrolled up. All right, such as these guys over here. So early cell phones. And then we move over to the right. And I'd ask, and I'm guessing probably no one knows the term that they use as far as the category of electronics for these gizmos right here. This says Pilot, so a Palm Pilot. This says Newton on it. I kind of remember the name, but I actually never owned either of these. But these were called PDAs. A personal digital assistant, so it had a calendar and notepad capabilities where you could send yourself notes and you could keep your calendar there and you could store your phone contacts and those kind of things. So it had a lot of the things that our modern smartphones did, but it wasn't on the internet and it wasn't a phone. So again, calendar, organizer, those kind of things, instead of literally in your pocket carrying a little pocket calendar with a contact list or whatever. Hey, you just do it in this electronic form, And then down below, let's see, we have, well, come on now, there we go. Over to the left, MP3 players, and then to the right, phones. And it's, of course, I was a young man during these days here, and I don't consider myself, a research fellow material, I guess. I've come up with a few decent ideas here and there, and made a small amount of money selling some apps and different things like that, But I'm not really interested in all of the business efforts that it would take to market things and all the rest of that. So anyway, I've always been an Indian instead of a chief. And hey, the good news is if you're in that same category in terms of your interest or skill set or whatever, they need an awful lot of Indians and not as many chiefs, so that's kind of okay. And but even I remember all those years ago, back in the 90s, when I would literally, have pocketfuls of electronics at various times. Oh yeah, another thing I could have thrown in here, which I have right here, was another thing I remember lugging around. And even I, not the best research fellow around, so I got a little jump drive here I used to transfer our video files from this PC upstairs to my office then so I can upload them to Google Drive. But I remember back then and thinking to myself, one of these days, somebody smarter than me is going to take all of these things and integrate them together, into, of course, today's smartphone, which has all of that and more, And hey, sure enough, I was right, but of course, I guess that was pretty obvious, But here's the thing about all of these devices. So it's kind of a similar story, but the numbers are kind of reversed in a way. So those early computers back in the 40s, there were companies that sold a small number of very expensive computers, a small number of very expensive computers. But you calculate that product, and it's a lot of money, okay? On the other hand, so that was the 40s, here we are in the 90s, and we sold a tremendous amount of very inexpensive computing devices. But still, that product was big. Okay, the product was big. It's just which one of those two factors was big and which one was little. Instead of a small number of expensive machines, we had a tremendous number of very, very inexpensive systems. But the weird thing was, they had the same problem programming the dadgum things that they did in those earliest days of programming when they were writing, well, not machine code, but assembly code. See, the thing is, these electronics over here, they run on these tiny little microprocessors that cost 30 cents a piece, and they're so small and they're so inexpensive that no one ever even took the trouble to come up with a decent development environment where you could write programs for those things in a high-level programming language. So instead, these things were programmed, oh my goodness, this was the 90s, and these things were programmed in assembly language. In assembly language, just like they did 45 years earlier, back in the 40s and 50s and so on, you know. And then the exact same problem came around. So, you know, you're Nokia or whoever, and you know, whatever it is, the CPU that you use in your phone, and again, it costs 30 cents, and it'll run at a certain clock speed, how so much power, could address a certain amount of memory and so on. And then you get the knock on the door, and the salesman comes in and says, hey, we've got a new microprocessor from our company. Instead of 30 cents a piece, it's 20 cents a piece, and it's 10 times as fast, can address 5 times as much memory, and so on. Hey, that sounds good. Oh, yeah. But I've been paying an army of programmers for the last 5 years to program these dadgum things in assembly code, and I'd have to rewrite every bit of it. Doesn't that sound like a familiar problem? It's the exact same problem they had 40 years earlier, all right? So what James Gosling recognized was, you know, it would be really nice if we could write a piece of software that pretended to be hardware. So it's a virtual computer, a virtual machine. Let me draw you a block diagram to kind of explain this. All right, so we're going to come over here and here and here. All right, so you'll see plenty of these block diagrams in your studies of computer science. You go that route, you know. All right, so let's zoom in on this bugger here and come up here. Okay. All right, so a block diagram. Here's this, and here's another one kind of just like it over here. All right. And then, okay. So this was a computer and its software. Again, we call each of these block diagrams. We're going to say this is, let me slip my little pin here. This is before James Gosling's idea. And anyway, we have the computer hardware here. We have the computer hardware. And again, this hardware, the amount of power in this computer hardware, this microprocessor, the amount of memory that was there is very small. So you couldn't run Microsoft Windows or Unix or something else like on it then, because you just didn't have enough room in memory. You didn't have enough CPU power to do so. So the application programs, they had to talk directly to the hardware, back and forth. And so you had to really understand how this hardware works. You could talk directly to the hardware and make it do its wonderful things, you know. And that's how all those little consumer electronic devices were programmed, was with, now these programs were written in assembly language, and they talk directly to the hardware. So you move the hardware, you replace the hardware, you have to replace the programs, just like we talked about. But James Gosling's idea, so this is Gosling's idea. Was, okay, well, we're going to still have hardware, of course, but let's add a little layer of software, and we're going to call it a virtual machine. Virtual. That means it's not really what it says it is. It's kind of pretending to be, if you will. A virtual machine, a virtual computer. And then the application programs, they just need to be written to talk to this virtual machine back and forth. And see, then the beauty of all this then is, let me go ahead and I'll do the following, you know. Move this over just a skosh. And then the nice thing is, and then, for dramatic effect, I'll come up here and get a different color, I guess. All right, so we'll do the same thing. Hey, where's my color selector? Well, this is disappointing. Let's see. Is it after the fact I need to do it? Maybe that's what it is. Give me a chance to change the color. And hey, there we go. So there we go. So a new hardware vendor comes along. And so we'll now switch over to our pen and pencil. So you get that knock on the door. Someone says, hey, I'll even do this. Okay. And so we have Oops Hardware. Number 2, if you will. All right, a different hardware vendor. Well, all that we need to do then under that circumstance, there's only one program, only one that needs to be written to talk to this hardware 2, and it's this virtual machine. So they would port this one program over here, and then the nice thing is, all of these things can be copied over unchanged. And since they talk to the virtual machine and the virtual machine talks to the hardware, you know, we could have drawn these little arrows here, and also, I guess, the virtual machine talks back and forth to the hardware, both over there and over here. And anyway, so that allows for portability. And man, that was a wonderful thing now, just like it was in the 50s then, in allowing programs to be written once and executed over and over and over again. So that, anyway, that was his goal. That was James Gosling's goal then, was to create a little layer of software that had this virtual machine. It was also sometimes called a runtime environment. All right, so let's put that in our notes here, I guess. All right, so James Gosling's wonderful ideas then. He wanted to add, to implement a VM, which is a virtual machine, also called a runtime environment. All right. And anyway, he launched that with some success, and it was just real early on. It was real early when this first kind of hit the market and was starting to make some gains. And anyway, the area that he had targeted us for was these consumer electronics. But man, oh man, did James Gosling get, and Sun Microsystems, they get lucky. Because it was right at that time in the mid-90s, when something else big happened in the world of computers. Something that you use every day, all the time. Yeah, well, you know, Google, soon after, you're right, that was just a little bit later, but back it up a little further. Now, to be clear, when was the internet created? In the 70s. It's funny, if you're old enough, you might, if older people, you might ask your parents about this, they might remember at one point when Al Gore was being interviewed, and he said, yes, it was at that time that I took the initiative and invented the internet. Okay, of course, he's a politician, from Tennessee. And anyway, those, I think, were his literal words. He took the initiative and invented the internet. To my knowledge, he knows nothing about computers, computer science, electronics, nothing, So he didn't invent the internet. I think he voted on some government measure to help give some additional funding for it or something else like that, But it was well after the actual internet had been created. And when I was your age, the internet existed. And so, I was logging into Unix systems. You could remotely log into another system, and you could transfer files. And also there were some discussion boards and those kind of things, that were available. So a lot of the things that we really like about today's internet were available then. But one thing that we didn't have until the mid-90s was a web browser, which is a piece of software. But anyway, we didn't have a web browser. And then when the web browser popped on the market, like Netscape Navigator and some others then in the mid-90s, then that was wonderful. And the first web browsers, they supported text and graphics. So in our discussion of interesting or important points related to Java history, we ought to mention, the World Wide Web, the first web browser. Browsers, we'll say browsers because multiple followed really, really, really fast. But the first web browsers, they supported text and pictures. So, hey, you could, create a little web page and you could share information about your business and when it's open. But it's all static contents, all right? It was all static at that time. But it was still, useful. But then James thought, this runtime environment that we have here, and then this Java programming language that goes along with it then. So you write Java programs to talk to the runtime environment. So if we took and integrated that runtime environment into a web browser, then programs could be executed inside a web browser. And that was huge. Oh my gosh. So they did that. So the early web browsers got together with James Gosling and Sun Microsystems, and they ported that runtime environment where instead of it, like over here, instead of the runtime environment, here, just talking directly on simple little microprocessors in these consumer devices, instead, this runtime environment, or this virtual machine here, now it exists as software. It's software here also, but now it's software that is embedded as a plug-in into a web browser. And then these application programs that could run anywhere as long as there's a runtime environment, as long as there's a virtual machine, those programs could execute inside people's web browsers, and now that allowed for very dynamic content, all right? So now things are being generated at your computer that you're running, dynamically there, instead of static content coming down in. And man, oh man, so although that really wasn't James Gosling's intent, he just got very lucky. I think that term is serendipity, when a couple things kind of come together in a wonderful combination. So in the end, Java programming language, James Gosling and so on, their success was less from the consumer electronics than it was integrating the RTE and the Java programming language into the web browsers. So all right, so we'll just put one last, put the RTE/VM into web browsers to allow application programs to run in people's web browsers. And that took off like crazy. And in no time at all, the Java programming language was one of the most popular programming languages in the world. And again, it still is to this day. It's been in and out of #1. It's never been below #4 in the last 3 decades. All right. So there you go. There's our history of programming languages in general, and then more recently, the Java programming language itself. How are we doing on time? Yeah, sure enough, about 45 minutes in. Let's see. Can you guys take questions on that? All right. Well, I'll tell you what, it's a little early on the clock, but today's going to be a little shorter day than some, and certainly in terms of we're getting ready to shift gears then and start talking about our first Java programming lab of sorts then. So I think it's probably a good time for a break. So let's do that, just that. Let's take 3 or 4 minutes, take a break. We'll come back and we'll start talking about our lab 1. We're back from our break, so now let's start talking about our programming lab 1. And certainly if you're wondering, gee whiz, have I learned enough to write my first computer program yet? Well, we haven't even started talking about that at all. We're going to just begin that old journey, I guess, today. And this is not uncommon. Your first lab here, I'm going to provide you the program, and you're just going to practice using the development environment, the editor to type the computer program into the system, and the compiler to compile it and turn it into machine code, and the runtime environment. Oh, we talked about that term a minute ago, in order to execute it. So I'm going to provide you the code. It's just going to be a short, fairly simple little program, and you're just going to crank it into the system in the right location and get it compiled up and so on. So for those that are listening from home, what we'll do then, let me see, I might need to change some permissions and make that available real quick. Let's see here. CD to pub PF1. There's that. All right. And okay, there's that. And now, so you guys listening from home, I would suggest go to my, on the server, on the web page, go to my home directory /PF1 lab 1. All right, boy, not much here in the form of instructions, but the main thing I wanted to pull up for right now is what we're going to have you do for this lab is type in the program, all right? And for you guys here in class, I've just handed it out for you. For you that are listening from home, what you might do is click here and then print this out, print it out. So, of course, I could have just pulled it up. So how we got here, of course, is we just went to PF1 Lab 1 under my home directory on the web, and then click here. So I could have you guys here in class also just pull this up on the web. But, well, we're going to go ahead and start talking about what this program does and how it works today. All right, now we're going to give you the mile-high view. We're flying in a plane 30,000 feet, just going to kind of point out some of the highlights and so you understand a little bit about it. And then what we're going to do, you're going to type it in, and we'll grade that as your very first lab again. Just really practice using the development environment. And then we're going to jump in starting our next class period, our next lesson, and we're going to start going over all of these things in much greater detail. So do understand that for today, all of this is going to be mysterious and new to you and everything else. Even after I hit the highlights, it will still be 90% a big foggy mystery, you know, and so on. But trust me, then we're going to back up at the next class period, and we're going to start, and we're going to write the smallest little program possible that will just compile and run and add things to it and explain them in detail as we go. So bear with me, you know. Ultimately, that's kind of the way it goes on learning some of these things. At first, you see it's very confusing. We go over it again and again and again and again, and it gets less confusing as you go, so just kind of expect that. So what the heck, let's go ahead here. And again, the advantage of me asking you guys at home to print it out for you guys here in class that I've provided a printout is as I kind of describe what these various parts of the program do, you can write it on your piece of paper, which could be kind of nice then, okay? So let me pull up the lab here, and we'll just talk about it. So let's go here and here. And we're going to kind of just talk about the lab for now because we're doing just fine on time. Okay, lab1.java. All right, so, you know, if you write on it, make sure you don't, I don't know, write so much on it that you obscure anything that make it harder to read. Of course, if you did, you just have to pull it up on the web. But all right, so I've just pulled it up here in VI, and we'll just start at the top, and I'm just going to, again, just kind of hit some high points, if you will. All right, this import statement, again, you might make a little note actually on the sheet itself, would be as good as anything, perhaps, or, you know, whatever kind of makes sense to you guys. But this import statement makes some code provided for us by the Java language available to our program. So sometimes when you're writing a program, you say, you know, I'd like to take advantage of this feature that the language has, but it's not visible, if you will, to your program until you use an import statement. So it just kind of makes some other code visible, available to our program here. So that's what an import statement does. So we're importing something called java.io. I wonder what I/O stands for. Can y'all guess what I/O stands for in terms of computing? It's an acronym, 2 words. I think it might be one of those you say, oh yeah, of course. I'm guessing y'all have heard of the term. I/O. Boy, this is just computer 101 stuff. Input. And what's the other one? Ah, very good. You guys are all right. Input, output. Exactly right. So we're doing some input-output. Now, output is where our program will display something to the user. Input is where our program needs some information, well, either from the user or from a file or from the network or, you know, at some other device or whatever, but I/O. So in order to read something from the user, we have to have this import statement there. Hey, these next few lines here, you notice we have a blank line just for readability. All of these lines here that start with // we can say that those are comments. Hey, notice, in fact, back here, let's see, where do I have to go to get there? Oh, yes, back here in Word, over here. So when we're talking about writing programs in assembly language, I pointed out, hey, this is it. Here's a machine code program, start to finish. But when we went to assembly language, it had some blank lines and it had some comments here and also these things here. These are comments. The compiler ignores them, but they're meaningful to the programmer that's looking at this text file, okay? Hey, so that's kind of neat. So our assembly code, we indicated a comment with a £, but in Java, you indicate a comment with a pair of slashes, forward slashes, okay? So to be clear, from this point forward, you know, just Unix, when we talk about Unix, a slash means a forward slash. Java, the same thing. All right, and okay, right here, this very important line, this is called our class header. So you might make a note over to the side. It is a class, C-L-A-S-S, just like that, header. And then underneath that here, this one here, notice has the word main in it. This is our main method, M-E-T-H-O-D. It's our main method header. Let's talk about what this program does real quick, I guess. So I just wanted to give you a simple little program that does some simple little task or whatever, you know. And all that it does is it calculates, it reads in some numbers from the user, and it calculates their average and prints it out. As simple as that. So, you know, you can imagine what kind of logic does it take to do that. You know, just imagine if you're wanting to help a friend of yours average up some grades or something like that. You're the one to calculate. Okay, go. Give me a number, and you add it up, and you add it up, and you add it up. But in addition to adding the numbers, you have to calculate the sum of the numbers. What's the other thing that you have to keep track of in order to calculate an average? That's right. How many numbers? So you need to calculate the sum and then the number of the numbers. And so we're going to kind of see both of that here in this little program. And again, we'll kind of hit the high points there. But all right. Hey, you know, look at this here. This is a comment. Declare your variables, or declare our variables. And then I actually do that right here. Kind of a funny little piece of trivia, I guess, about my time here as an instructor and as a faculty advisor to young, budding computer science students. It's not unusual for a student, maybe a parent or two, to show up in my office and express some interest in programming. And, you know, a lot of times they'll ask, have you ever done any computer programming? And the most common answer is no. You say, have you ever seen a computer program? You know anything about it? The most common answer is no. So it is kind of funny that I want to be a computer programmer, but I have absolutely no idea what it actually involves, you know. But, you know, just from what you see and hear in the culture and so on, computer programming, I guess, sounds like it might be a good career path, you know. And, you know, sometimes they'll ask me, what is computer programming like? And it's kind of hard to give them a good answer in a very short amount of time, because it's something kind of unlike anything that you've ever done before. But the closest thing to computer programming that most students can relate to is algebra. And specifically, everybody, and I know this as an instructor, as a math instructor, everybody's favorite part of algebra is word problems, the famous word problem. Of course, I do see some students grinning or laughing or smirking there at that comment, because I know from many years as a math teacher, especially when you're teaching math to non-math majors, you know, and word problems are always reviled, they're always hated, you know, but anyway, I remember, you know, taking algebra all those many years ago, and solving word problems from dear Miss Springer was my teacher. And I remember one thing, first thing we need to do, rule number one, you know, of course, read the problem until you understand it and so on. But once you put pencil to paper, I'll just ask you guys if your memory of the step one when it comes to putting a pencil to paper and solving a word problem that old Miss Springer taught me and I taught my students, what might that be? That's exactly right. Very, very good. Yeah, knowing your variables, writing down your variables. And that's so I literally do remember, good job, Talton, I do remember my algebra teacher all those years ago. Step one, I mean, obviously after you've read the problem and so on, but when you're getting ready to start to solve it, you have to define your variables. You know, a lot of times you'd use X, Y, and Z and so on in algebra, you know. Let X equal the speed of the train or the height of the tree or the age of the boy or whatever it happens to be, you know. And then you define the other variables, you know. And why did we have to define the variables? Of course, in algebra, it's because you start writing equations next, and then you solve the equations, and ta-da, X equals whatever. And it can be the case that, okay, I know what X is, but what did X represent again? And you look to the top, and hopefully you wrote it down. But anyway, so sure enough, just like in algebra and programming, we need to define or declare our variables. Not only do we say, you know, variable whatever, you know, represents some quantity, we also have to give a data type. Integer, string, double, that's a floating point variable there. You know, hey, so if this program is going to average some grades. If I average a bunch of grades, why might the average be a floating point number? If I'm averaging a bunch of integers, well, because when you calculate a quotient, you can pick up something to the right of the decimal point there. So even though, yeah, I'm going to average a bunch of integer grades, and I'm going to count them as I go and calculate a sum, but eventually I'm going to divide the sum by the count to produce the average, and the average I might pick up a decimal point, you know. So double is a floating point type. So in math class and word problems, you didn't have to specify a data type like we do here in programming. You just said let X equals, you know, whatever. But so a similarity there. And of course the other big thing is in, you know, in mathematics and in programming also, you have constants and variables and expressions, and you know, you're writing out formulas and so on, you know. So there's a lot of similarity with algebra and specifically with word problems and so on when you're writing programs. So anyway, here we are, we're declaring our variables in a very formal way. And unlike algebra, where if you do it or not, well, you can still go ahead and solve the equations and maybe get an answer. But of course, here we have to write our program so that the computer can understand it. We're going to have to compile the program, where we'll check it for syntax and so on. And if you start using variables that you have never defined and never declared, the compiler is going to slap you on the hand, give you an error message, and your program will not compile until you fix that problem. You know, so that's one thing we can mention. There's always an appropriate time for me to do so. It popped into my head now. So when we write our programs, We know what we want to do, and we understand the problem, but we have to explain the problem in a simple enough way that a lowly computer can understand it. And dumbing down your solution to where the lowly computer can understand it is going to be a challenge. And that seems kind of backwards, I guess, because, you know, we're used to thinking of computers as being these brilliant things. And thanks to software, in many ways they are. But when you're the programmer, you're talking to the hardware, well, in our case, to the virtual hardware, the virtual machine that talks to the hardware. And those things are pretty simplistic. And they have a certain language that they speak. And if you don't speak their language, it rejects what you've got. So we have to dumb it down. So now's as good a time as any. Okay. Pro tip for today. This might be our first pro tip this semester. And this is also, this is rule number 1 for computer programming. All right. Boy, I skip letters all the time. Here we go. All right. And that is, we'll do this in boldface. Computers are dumb. All right, so that's today's pro tip that we must remember, because you are going to find it aggravating sometimes to dumb down what you clearly understand, because it's not that difficult, and yet the computer can't understand it, because ultimately, and then now here we're really talking about computer hardware. Computer hardware, it doesn't understand much of anything. Now, it can do some very, very basic things, including arithmetic and some other kind of similar things, very, very, very fast. So computer hardware is good at doing very simple little calculations, extremely fast, but beyond that, it ain't good for much. Everything that makes computers appear smart is software, And when we're writing our programs, we're not writing it on top of layers and layers of software. It's pretty close to the hardware, and so we have to speak the computer's language. And we need to remember on those aggravating days when you can't get the darn thing to compile or run right or whatever, well, that's because computers ultimately are pretty dumb. All right, so there's that. Let's see, so we have declared our variables, and here we are initializing some of these variables. We're giving them a value. So our sum and our count, we initialize both of these variables to 0 because we're getting ready to start counting and summing and so on. And so we're going to use these two variables for that purpose. But we need to make sure from the get-go they start out at 0, and then we're going to add 1 to this count and add our grade to the sum as we go in a looping process here. So we need to start these out. And again, kind of like algebra, you know, now to be clear, doesn't this kind of look like algebra? Of course, you know, algebra, it might look a little more like, all right, let's pull this guy up over here. Oops, and scroll down. Okay. So algebra, we certainly have something that could look like this. Here we got that. So, you know, x equals 0. You know, we're solving an equation and we end up, well, we can come up with a more exciting number than 0, I guess. Let's do that. X equals 5, whatever. So we had an equation and we eventually got to here. Ta-da, we're done. Or it might have been the case that we're working along solving the equation and we ended up with a variable over here and the constant over here. Also, ta-da, we're done. So we would say that these are equations. And we like these equations because we have isolated the variable. We have just a variable on one side and just a constant on the other. So we have solved an equation. And so anyway, this is an equation in algebra. But to be clear, this looks kind of sort of like an equation. Well, it's got a little semicolon on the end, but it just looks like an equation. But well, it's not an equation. That is an assignment statement. So you can put a little note there, you know. These are assignment statements. I am assigning a value to a variable. I'm assigning the value of the constant 0 to the variable's count and sum. So you have to have the variable on the left-hand side of, and this is the assignment operator, the little equal sign. You know, it is the equal character, if you will, on my keyboard, but its role in this program is not an equal sign, it is the assignment operator. You use it to assign a variable, which has to be on the left-hand side of that assignment operator. And we just talked about earlier, if you're going to help a friend average some grades, and you had the calculator, and he was looking at his grades, and he was calling them out, you'd have this repetitive process. Give me a grade. I add it to the sum. I add 1 to the count. You give me a grade. I add it to the sum. I increment or add 1 to the count. Well, in our program, we're going to do the same thing here with what's called a while loop. So I am going to over and over and over and over and over again, I'm going to do the following. Look here, print. Print. Well, I've got to talk about print again here. This print, we call this a print statement. This print statement, we're prompting the user. This is going to display on the user's console, on their terminal, on their little putty window, enter a number. We're trying to get the attention of the user, telling them to enter a number. We also tell them when you're done entering numbers, you can tell me you're done by entering a -1. Because -1 is not a valid grade, and that's my promise to you. I will never give you a -1 as a grade in this class, okay? So anyway, so all of the, I'm kind of inconsistent. I'm calling these grades, but I should say enter a grade. But anyway, enter a number. And then we're going to enter a number and enter a number and enter a number. And then when you're done entering numbers, just tell me that by entering a -1. But check this out, the word print. Print? Where does that come from? You know, we've got some printers out in the hall. I got a printer in my office and next door. Does that mean something's going to get printed? Once again, here we are in week 3, early on, and we have to go back. Why do we call that print? Do y'all know why we call it print? Y'all, yes, y'all know why we call it print. Because of these guys. Okay. So early computer programmers, they were working on these paper consoles. If they wanted to display the results of their program, they would print it literally to a printer. And so that just became part of the programming mindset. You print your answers. Now, yes, back then, it literally, dot matrix printer, and it would print out on the piece of paper. And then they rolled in the CRTs, and then later the flat screens and everything else, but the terminology stuck. So to be clear, in programming, when you talk about printing something, you're generally not talking about sending it to a printer. Instead, you're talking about displaying it to the user. Okay, and why is that? Because of those old guys 50 years ago. Isn't that funny? And it just stuck, and we passed it on and passed it on. And here we are all those years later, and we still print, in this case, a string literal, a string constant here, and that just means display it to the user. Then we're going to read in their grades. Kind of a two-step process. We'll talk more about that later, but we're reading the grade or the number from the user. And now we're going to check. Hey, check this out. This is an if statement. If that grade that the user entered was a -1, we need to bail out of this loop. We'll talk about this also in greater detail later. I'm just going to hit in the high points. And if it's all mysterious, well, it's assumed to be the case. Hey, now, here we go. We can look at these two statements here. And what we're doing, check this out. Sum plus grade and count plus 1. You know, just like how do you average some numbers? You give me a number, I add it to the sum, and I increment, I add 1 to the count. That's what we're doing there in those two assignment statements. You know, this was an assignment statement up here. On the right-hand side of the assignment statement, I had a constant, the integer constant 0. Here on the right-hand side of this assignment statement, what I'm assigning to the variable count is the result of this expression. Boy, it's nice that as a computer programming teacher, most of my students have just recently been through college algebra and so on, and they understand constants, variables, and expressions and so on. So anyway, we evaluate this expression, we take the result of that expression, and we assign it to the variable count. So count gets updated. Same thing down here with sum. We take the sum, we add the grade to it, and now we update the sum. Now the sum has that new value. Hey, down here, just for the heck of it, we're going to go ahead and print what's the current count and sum inside the loop, so we can kind of see a running total as we go. Anyway, this little curly brace marks the end of this loop. See, this loop starts at the open curly brace. It ends at the closed curly brace. So here's our little loop. It's kind of the heart and soul of this program. We prompt the user, we read in the grade, we add it to the sum, we increment the count, and we keep doing that until the user enters a grade. That's our secret little code here that they're going to tell our program that they're done. So when they enter a -1, we break out of the loop, and we come down here. Hey, look at that. We calculate the average, and we print it out. So even though there's no way in heck that I would expect you guys to be able to write that program, hopefully you kind of look at it and, you know, just based on a little common sense and so on, kind of sort of understand vaguely what's going on with some of these things here. So now to be clear, the program that I gave you, and this program over here, which, here, okay, yeah, this program here, which I provided my students that are watching this from home, it does not have any errors in it. All right, so it is a perfect, we call that golden code there. No compiler errors, no logic errors, works just fine. But also to be clear, after you type it in, you might pick up some compiler errors and so on. So we need to show you how to compile your program and go from there. So we're going to do that now. How are we doing on time? From 9 to 11:50. Oh, we got plenty of time. Okay, which is good. So let's do just that. So I have this typed in. So what I'm going to do is I'm going to introduce some errors. I'll tell you what we'll do. I'll go draw a picture of how to compile it first. And we're done with that. All right. Close, go. Well, it doesn't want to go away for whatever reason, so I'm done with this also. Is that going to go away? Okay. Let's see here. So let me do the following, and we'll show you kind of what we're doing when we're compiling our program. There's that, and this, and here. Okay. So eventually, you're going to be inside your, all right, so your home directory /PF1. Now to be clear, that's a separate directory from your Unix directory. So your Unix file system lab 2 and your VI lab that you just completed are down over here. But we're done with Unix now. That was just learning the development environment. So from now on, you're going to be working under your PF1 directory, and it's not there yet. You'll need to create it. You'll want a lowercase lab1 directory. And then you will create, using the VI text editor, your first program, which is capital lab1.java. Unix is case sensitive, and for the most part, Unix and Linux, it likes lowercase letters. Why? Because we're all lazy, I guess, and we don't have to hold down that shift key to type things in. But do note, this is an uppercase L. We'll talk about why that is our next lesson, but for right now, PF1 is uppercase. Well, that's an acronym. There's a reason for that. But lab1, all lowercase. Here, lab1.java, well, it's all lowercase except for that first L. So do make a note of that. The instructions specify, we can pull that up here real quick. All right, here, oops, the wrong one. That's from a different class even. Okay, so if we go back, it tells you under your tilde PF1 lab1 directory, you are going to edit a file called capital L lab1.java. So you will create this file with VI. Once you get it typed in, now you're ready to compile it. Okay, so you're going to invoke a program that's going to scan this thing here for syntax errors. If there are errors, it'll print out a message and tell you that you got a problem on this line number and so on, and then it'll abort. It will not create the executable. All right, so eventually, you're going to take that file and you're going to type Java C, that's all lowercase, Java C for Java compiler, and then lab1.java. So make a note, this is the syntax for the Unix command you have to type in. Java C, all lowercase, the word Java with the C on the end. So that's the command. And when you do that, and when it's eventually successful, it'll create a file for you called lab1.class. This is your executable program here. That's the executable. It does not run on the native hardware. It has to, why doesn't it run on that native hardware? Guys, I'm trying to remember if I even still have that picture here. I don't think that I do. It doesn't run on the native hardware because it runs on that runtime environment, that virtual machine. That was the whole thing about Java. Is these programs don't run directly to the don't talk, if you will, directly to the hardware. They have to be executed inside of a runtime environment. Well, how do we launch? How do we execute the runtime environment? Well, that's our next command then. So then we're going to type Java, so to run the program. So this is to compile. And then to run, once it has been compiled, all right, to run Java space lab1. Let me let y'all type that in, then I'm going to tell you something that you need to stress, that I want to stress here. This is important enough, and since my writing is so sloppy, and so I might go and duplicate this in my notes real quick here for you guys also, just for the heck of it. All right, so to compile, or we'll say our lab1, it's going to be Java C lab1.java. to run our lab 1, we'll do it this way. It's going to be Java space lab 1. And then I'm going to go ahead and come over here and put a little note. Note that there is nothing after lab 1. Students sometimes want to type .java at the end of this thing, or .class at the end of this thing. So no, it's just lab 1. It's just lab 1. And we're going to make that bold just to kind of stand out. There's nothing after lab 1. Here there's something after lab 1. It's lab1.java. So here you're typing the file name. Lab1.java. That's the name of the file that contains your program. Down here, this is not a file name. I do not have a file named lab1. I have a file named lab1.java. I have a file named lab1.class, but I do not have a file named lab1. But anyway, when you invoke the runtime environment, and Java is the program that contains the runtime environment, you specify the name of the class. And anyway, the name of the class is just lab1. Why is the name of the class lab1? Well, just for the heck of it, since we're here, look at this. Why is the name of the class lab1? Because our class header. So check that out. Class lab1. So when you're running the program, you're specifying the class name, not a file name, but the class name. So we'll talk more about that the next lesson, but we're just, what the heck. We'll mention it now. We'll mention it again then. Pretty soon it's going to stick. All right. So there's where we're headed. Questions on this little process. We edit the source code. We compile it with Java C, lab1.java. Now, we can't run until there are no errors and it actually creates our class file. But all right, let's demonstrate that then. And we're going to also introduce some errors and so on. So, okay, so over here we go. And I probably have a class. Oh, I don't. That's good. I don't have a class file there. So I've edited my little program, and let's see if it will compile. So Java C, lab1.java. Sweet. All right. No news is good news on Unix commands in general for our compiler also. It didn't complain about anything. And earlier I typed ls and I had just my source code. Now I type ls. Oh, look at that. Now look at that. I picked up another file. We can look at the dates on them here. All right. So lab1.java, well, I haven't edited that since last semester at this exact same point in the course, And we're going to make some changes to it today here, though, on the other hand. So this darn source code is 5 months old. But ta-da, I've got a brand new executable here then, a brand new executable. That contains what's called the bytecode. Hey, that's an interesting little piece of trivia that we can mention. All right, what the heck? We'll put it back over here with our Java history stuff and so on. All right, so Java's executable code is called, for whatever reason, James Gosling had to have things different, I guess, bytecode. All right. So it's not actual machine code. It's machine code for that virtual machine, if that makes any sense at all. Thinking about that picture we had there with our block diagram. And anyway, in Java they call it bytecode, kind of a goofy name. All right. So we're doing great. So we have compiled our program just like our little drawing suggests over here. All right, to compile you use Java C lab1.java, and I did just that, and sure enough, it created my executable. So the compilation process creates your executable. And then to run it, well, just like my notes say, Java lab1. So I hit enter, and then the Java program launches. That's the runtime environment. It reads in my lab1 class file and executes it. Looky there. Enter a number. -1 to quit. Where's that come from? Right here, right? So there it is. There's this prompt. We would call it prompt. We're trying to get the attention of the user. Hey, knucklehead, pay attention. Enter a number. Oh, okay, there we go. So we're averaging some grades. 80. Enter. So it updated the count. It updated the sum. Went back to the top of the loop. Prompting me again, enter a number. Hey, I'm doing better now, a 90 on my second grade. All right, so I hit enter. It incremented the count. It updated the sum, went back to the top of the loop. It's asking me again, enter a number. Hey, better than ever, how about a 100? So it's updating those variables as we go back to the top. That's all we got so far, just got these 3 grades. Of course, I picked those because they're easy to average. So I'm going to enter a -1 to tell the program we're done entering numbers. And of course, back to our code we referred just for the heck of it. Remember, oh yeah, when the user enters a -1, we're going to break out of this loop and come down here and calculate the average and print it out. There we go. All right. Simple as can be. All right. So there you go. And again, the code I gave you is, quote, golden code with no errors, but most students will manage to cram an error in there one way or the other, just, a typo, a misread, forgetting something. To be clear, a real common mistake, the most common mistake probably, is students, for whatever reason, they just skip that first line. They just omit that, just, because, I don't know, they just do. So make a note, don't forget that line. Okay, but let's go ahead and let's introduce some errors and how to fix them. Okay, so we're going to spend the rest of the class doing just that, or the rest of the time that we spend here. Okay, so I'm going to go in, VI, lab1.java. And the very, very common thing is, hey, this looks like an equation in algebra class. This is actually called an assignment statement. But anyway, statements are terminated with a semicolon. Just like in the, so to be clear, Java is a programming language. And languages have a syntax. There's a grammar. There's a grammar. The grammar is the formal description of a language. When Grandma and Grandpa went to school, they might have talked about they went to grammar school. They learned how to read and write correctly. All right, they studied the English language, and they learned how to put together a sentence, for instance. So programming languages, they are languages. They're just languages we're using to talk to computers, and they do have a grammar. They do have a syntax. And the syntax says that statements must be terminated with a semicolon. Just like in English, sentences must be punctuated, or must be terminated with a piece of punctuation, a period, an exclamation point, a question mark, or whatever. So I forgot my semicolon at the end of this statement. All right. So I save the program. Now we need to. So we'll try to compile it here then. All right. Oh man, good. Nice thing about Java, again, it's a wonderful programming language for your first programming language. It has good, descriptive, easy to understand error messages. So we tried to compile the program, and it says error, a semicolon is expected. Now look at this. Thank you, Java. It gave us the line number. It gave us the line number, just like we were talking about when we were learning VI. So remember that command, we can use :25. Boom, it jumps us right down to that line number. And look at this. It even displays that line number, and there's a little pointer. Right here is where I think that semicolon needs to go. It's trying to tell you, right here, you're missing a semicolon. It's really doing a very, very good job. Now, some compiler messages are better than others. This one's a wonderful one. Others, it's just impossible for the compiler to know exactly where the error took place. We'll talk about some of those also. So, one other thing I wanted to show you, ls-l. Now, to be clear, and this is... Well, I guess I could make a suggestion to Java. And James Gosling, he quit taking my calls, so I can't call him anymore. But the one thing I don't like about this is now I have updated my source code, and I tried to compile it, but it bombed. But the class file is still there. The class file is still there. But note that it's out of date. See, this was at 10:19, this is at 10:24. This class file is 5 minutes out of date. We would say that it is a stale executable. Stale, it's out of date, like a piece of stale bread. It's past its prime. Since the source code is newer than the executable, then the executable might not, in this case it does not, reflect updates that have been made to the source code. But since the executable is still there, if you just blew off this message, you could run the program, but you're running the old program, okay? So that's one of our programming rules. I'm not going to bother to pull it up, but on the internet, we had our late work policy and attendance policy, and there's a homework policy. And one thing in the homework policy, we didn't go over it in detail, but I am now, when you turn in your labs, your source code should be, your executable should be as new or newer than the source code. You don't want the executable to be older. If the executable is older, it is said to be a stale executable. It doesn't reflect your most recent changes, and that's not good. So don't submit work where your executable is older than your source. Now, so if they're the same date, if they display the same, that's okay. Because what can happen is you get out of the editor, you invoke the compiler, and it all happens very quickly. And since ls by default only displays to the nearest minute, or well, not to the nearest, but just to the most recent minute, that if you compile it in the same minute, we're going to say it's okay if they have the same timestamp on them. Now the truth is, There are options you can give to the ls command where it will display seconds also, but by default it's just hours and minutes. But anyway, we want to make sure that we don't have this where the source code is newer than the executable, where we have a stale executable, which we do here. See, some programming languages, when you invoke the compiler right here, step number one, it's going to remove this. It's going to remove the old executable. And that way there, when the error pops up, and then you look, there's no executable there. It got rid of the old one. And then there's no, oh, never mind, and you just go on, you know. So I wish that Java did that, but it doesn't. But it is what it is. So we've got to fix that error. So you remember, okay, line 25, I'm missing a semicolon. So we walk through our previous commands. All right, I'm in the editor, and once again, learning those shortcuts. Oh, yes, to jump to line 25, make sure in command mode, :25, enter. :25, displays down at the bottom. Enter, there we go. And more shortcuts. Oh yes, that's right, I need a semicolon at the end. We remember capital A will put me into insert mode at the end of the line. Capital A, poof, I'm in insert mode. There's my semicolon, escape, capital ZZ, and I'm out of there. Try again here, boop. There we go, ls minus L. So there we go, here's an example. I edited, and then I compiled, so the class file is a few seconds newer than the source code, but I can't really see that here. It looks like they're at the same time, but we're going to say that's okay. Again, there is an option that will display actually seconds and milliseconds, you know, on the modification time, but we want to make sure that the class file is as new or newer. You know, for instance, if just for the heck of it, if I compiled it again and then typed ls minus L, okay, so this certainly is fine too. Now we can clearly see the executable is newer than the source code, and we want it to be newer, but sometimes it displays the same when you compile right after you edit. Okay, compiler error number 2. Let's just keep knocking some of these out here before we wrap up today. And I'm going to go down, and I'm going to forget to even declare a variable. So I could just remove this line of code, but instead I'll just comment it out. So now I'm using a variable called count, which has never been declared. All right, and you know, in algebra class you're supposed to declare your variables. In programming we are also, and here the compiler is going to nail you if you don't. So all right, we'll compile again. All right, so there's a couple different places in our code when we are incrementing our count, when we're updating the count, and also when we're using the count to calculate the average. It says this variable count might, this is not the best error message, might not have been initialized. It was never even declared. But that's kind of okay. But hey, you know, one thing to point out, the previous compiler error, it told you what line number, where the line number was that you needed to make the change. Here it just tells you where this unexplained, unexpected variable popped up out of nowhere, but we don't necessarily make the change on line 39 or line 48. We just have to make sure and make that change somewhere previous to these two lines, right? So here's a good example of, it doesn't always tell you the line to go to fix the problem. It's just these are the two lines where it first was able to detect the problem. Oh yes, I forgot to declare. And again, this is not the best message. It should say, it has not been declared. But all right, fine. So we'll go back in, and we'll just skip down here. Oh, that's because oops. Here's where I'm actually declaring. Oh, excuse me. Oh, I spoke wrong. I spoke wrong. What I commented out was the initialization. I spoke wrong when I said it hasn't been initialized. That actually was the problem. What I commented out was the initialization. Let's fix that, and then we'll get rid of the declaration. I got those two mixed up. All right, so we will compile. Ah, it does compile now. And anyway, here's the other message that I, in my mind, switched gears to. I was thinking we had commented out the declaration, but no, we had commented out the initialization. Give credit to the compiler. It was right, I was wrong. It was the initialization that was missing. Now the declaration is going to be missing. So let's see what it says here. Oh my goodness, all right. So hey, this is an important point to mention. I have, down here, we skip to the bottom, 5 errors. I commented out one line of code and it gave me 5 errors. Everywhere in the program where count appears from that point down, cannot find a symbol. A symbol is the name of a variable or maybe a method. So look at these messages, you guys. This is a big part of PF1, is learning how to understand these messages and learning how to correct your own compiler errors. And so by the end of this semester, you should be pretty darn good at fixing your own compiler errors. And you get that way by studying these things in some detail. So the error message here on line 25, there is it can't find a symbol. So you guys need to remember a symbol is the name of a variable or a method. Well, then here it is. It's pointing out that symbol. And notice down here, the symbol that it can't find is the variable count. Okay? So a symbol might be a variable, it might be a method, but it's explaining here, in this case, the symbol is a variable. It's kind of weird. Why didn't it just say can't find the variable? Well, I don't know, but it is what it is. Anyway, it tells us that the location for this is inside our Lab 1 class. Oh yeah, well, we know that. Same thing here, line 39, can't find the symbol. It's pointing the count here. The symbol that it can't find is the variable count. Same thing on and on and on and on. So, okay. So, yes, once again, I had the initialization and the declaration swapped in my mind. The last one was correct. We had declared it, but we hadn't initialized it. Here we hadn't even declared it. But once again, it can't tell you where the declaration has to go. It just has to be somewhere prior to these lines. Okay? So it can tell you where it first detected the error, but it can't necessarily tell you exactly where to go to fix the error. But hey, we know, of course, hey, this is as good a spot as any. Of course, I could have declared count up here or down here or somewhere. As long as it preceded this statement, anywhere up here would have been fine. But this is a perfectly good spot here. Okay, so we'll get rid of the comment, which makes this line of code now available back into the program instead of being ignored by the compiler. Let's see if that fixed it. And it did. Now, one thing before we move on, we'll knock out a few more of these before we go, but notice that one error caused 5 error messages. Now, one thing that you need to think about, this is kind of a humorous little thing that we need to discuss so that you understand something about the compiler. The compilation process, the compiler, the program Java C, it actually goes through your program multiple times. It goes through the programs on the first pass. They call it a pass. I'm going to pass through the code once looking for these errors. If that's good, no errors, then I'm going to pass through a second time looking for these errors. If that's good, I'm going to go through again. Anyway, a lot of times there's going to be 4 or 5 passes. The compiler is going to go through your code 4 or 5 times looking for different errors at each pass. All right, so what can happen is you can have one compiler error. You have one compiler. Let's say on the first pass, you have no idea which pass the error was detected on. It doesn't display that information to you. But let's imagine that your program, when you compile it, will say that on pass 1, we'll assume on pass 1, there's one little error. There's one little error. And you fix that error. And then you compile it again, and then it gets 5 errors. Okay? Well, that's kind of disturbing. Gosh, earlier my program was almost perfect. It only had 1 error. And then I fixed that error, and now I've got 5 errors. So I will every once in a while have a student. I've had this happen a number of times, and I kind of chuckle, and we can all kind of chuckle at them now that we understand the issue here. So pass number 1, there was 1 error. They fixed it. They went on to pass number 2, and they picked up 5 errors. Those 5 errors were lurking out there. They just weren't displayed yet. They weren't encountered yet. But I'll have a student every once in a while that'll tell me, hey, I had 1 error in my program, and I fixed it, and then I got 5 errors. So that's not good. So I put that 1 error back. Okay, well, the 1 error got rid of the 5, but again, they were still lurking out there to be solved at some point in the future once you got rid of the 1 again, because you have to get rid of the 1 to get your program to compile on. So anyway, so in other words, the lesson learned is the number of error messages you get doesn't matter. It doesn't matter if you get 1 error or 10 errors, blow that off. And the other thing that's kind of related to that is just look at the first error. So make a mental note of that. When you get 4 or 5 or 6 error messages, just look at the first one and then jump back in your code and fix it. Because just like we saw just here, we fixed the error that was caused the first message, and it made all the other error messages go away also. Okay, so fix the first error first. Back in the day when I was learning to program, the computer systems were slow enough where it literally was the case that you'd edit your program and then you'd start the compiler, and you're working in the computer lab, and you tell your buddy, hey, I'll be back in a second. I'm going to run down the hall and drink a Coke real quick. I'll be back about the time my program finishes compiling. Okay. And, well, if it's going to take a bit of time for the compilation process to do its thing, then you might go ahead and look over the other messages and so on to see if you can, by any chance, fix a couple of errors at once or whatever. But for you guys, even though all of us are sharing a PC that's in a closet down the hall, and that is our quote server, which is kind of laughable. Because when I learned to program on a Unix environment, it was on a system that followed on from that one that Ken Thompson and Dennis Ritchie were sitting at. It was a DEC, digital equipment company, VAX, running Unix. And back in those days, I remember, because I ended up going to work full-time in that computer lab. And anyway, those DEC VAXs at the time were $50, $75, $100,000, all right? And even at that, when it came to compile your program, it would take 4 or 5 minutes, and then so you'd have time to take a little break and come back, and now the results are there, and so on. And here we are all these years later, and we're using a cast-off PC running Linux in the closet down the hall, and we've got 80 students sharing the same machine, and the programs compile in milliseconds, so pretty amazing stuff. So just fix the first error, don't worry about how many errors, and certainly never do like some have, and put an error back, because anyway, you got other errors that are still lurking out there. Let's fix some more errors, and then we'll wrap this up. Let's see. Other errors that are kind of hard for the compiler to nail down sometimes. One that comes to mind. So, you guys again know the difference between constants and variables and expressions. So, all right, my young friends, this is an integer constant, right? The number 0 there is an integer constant. If I had, I'll just come over here. So that's 0, that's an integer constant. Well, this is a character constant, and we would say that this is a string constant, okay? We might also call it a string literal. So they're all constants. They're not variables. They have a fixed value, just like the number 0 does. The character C, the string word there, hello, those aren't variables. They are constants. But anyway, so this here, you guys, our prompt. This is our prompt string. It's what we're displaying to the user to get their attention. Enter a number. Well, we marked the beginning of that string constant or string literal with a double quote. What if we forget the ending double quote? I don't remember for sure what Java is going to do here, but the truth is, string constants can span multiple lines. Well, if string constants can span multiple lines, the compiler might have a hard time guessing where the heck is this string supposed to end. It's just going to detect, hey, I got to one double quote, but I never got to its mate. That's an important thing. We can show you that also. That'll be next. Help me remember that. We need to show what happens when a parentheses doesn't have a mate, or a curly brace doesn't have a mate. Those things have to appear in pairs. Square brackets, parentheses, curly braces, single quotes, double quotes. They have to appear in pairs. So here we have a single double quote in our program. Actually, we might have multiple ones, but up here on that one line. So we will try to compile. Yeah, okay, so here, the error is an unclosed string literal. Now it's pointing to this. That's not the problem. It's just telling us, well, here's where the string literal started. It doesn't know where it ended, because it could have gone on multiple lines of text in our program. We know, okay, that started on line 31 we see there, colon 31. We know, no, this is more statements here. This is more code. Well, yeah, we know that, but the compiler doesn't. It just says, okay, here's the beginning of our string literal, and we don't know where it ended. We could certainly write a string literal that contained this stuff here if we really wanted to. Okay, but we know, okay, that's right. So we'll put a double quote there. That should fix that. All right, it did. Let's pull out some missing parentheses or curly braces or whatever. And how about, this one over here. We'll get rid of a parentheses. All right. So we got rid of a parentheses, and we'll try to compile. And hey, good job. They did a good job there. Look at that. Error. This is kind of a confusing thing here, but anyway. Oh, it's telling us a comma, a closed parentheses, or an open square bracket is expected. But look at the little arrow right there, which is exactly right. Okay. So they're on line 11. So back in we go. Good job, Java. That was a good message. We'll do that. And we'll remove a curly brace. Those are also easy to forget. We'll remove one down here. I'm going to remove this one. That's gone. So again, the compiler is going to say, okay, I got an open curly brace, and it's going to see that the number of open curly braces, the number of closed curly braces, they don't match up where they should. but it doesn't know. To be clear, the indentation here, that's for our human eyeballs as we look at this code. So Java doesn't know. It's going to have no idea where to suggest that we put the matching close curly brace here. It's just going to tell us that it found it open without a close. Let's see exactly what the message is. Oh yeah, so this is definitely not especially helpful. Line number 51. Here's line 51. What the heck line is it pointing at? What it's pointing at is this closed curly brace at the very end. It says, I got to the very end of your program, and the number of opens and the number of closes did not match. That's all it could tell us. And so that's an example of one that, well, it knew something's missing, but it has no idea where we intended to put it. So that's a little more work. You just have to then, well, I got to study my curly braces where they need to be because they're out of whack. All right. So, oh yeah, speaking of indentation, we'll talk about that, and then we'll kind of wrap this up, I guess. Oh, you saw me just right here. So to be clear, so on your homework, Lab 1 and beyond, I don't know if any of you guys are already in your spare time already grinding your program in, which if you are, then you are. But I'm going to make this clear that for Lab 1 and all of the labs to follow, our indentation, these are all multiples of 4 spaces. These 2 lines here are not indented at all. And then this is indented 4 spaces. This one here is indented 8 spaces and 12 spaces, and that's as far as we get. So our indentation that we're going to use are multiples of 4 spaces, not tabs. Just to make that clear, and then we'll put that in our notes. All right. Note, use 4 spaces for each level of, quote, indentation. All right. Now, students want to use a tab. Now, a tab, by default, expands to 8 spaces. But, you know, we had how many levels of indentation just in this simple little program? Well, okay. This is indented once. This is indented twice. This is indented 3 times. So, by default, a tab expands to 8 spaces. So if you're indented 3 times, you're skipping over the equivalent of 24 spaces. Your screen is only by default 80 characters wide. You're a third of the way over before you've typed the first character of actual code on that statement. That means you're more likely to get things wrap around, okay? Now to be clear, will VI allow you to change where tab is displayed at something smaller? Yes, it can. So you can tell VI, hey, I'm going to use a tab, but display it as the equivalent of 4 spaces. And that's cool, but guess what? If you send your source code file to someone else that doesn't have that setting, it's going to expand to 8, and I don't have that setting, okay? So it helps a little bit with readability. It's pretty common. That's a pretty common thing. Now, some integrated development environments, you can have it set up, kind of the best of both worlds, I guess, where when you type a tab, it inserts into your file 4 spaces. So you get to be lazy and just hit 1 key, but you still get the more flexibility, I guess, of using the 4 spaces, so it always displays the same. But it's a very small thing, and it's one of those little nitpicky things that programmers might bicker back and forth on which is better and so on, you know. But it's funny. I have just asked my students over the years, hey, if you would, for my sake, I guess, and because I think it's a little more widely used, use 4 spaces instead of tabs. And I had an enterprising student that a number of years ago, he did a little bit of reading, Googling or whatever, and he announced, and anyway, he had found some study or survey or whatever that had been done years ago, and he was proud to announce to the class that programmers that use 4 spaces tend to earn a little bit more money than those that use tabs. So, so there you go, take that. But that's what I'll ask you guys to use. All right, so all that you guys need to do for Lab 1 is, as the old instructions say here, type this file into this directory, compile it up, run it, make sure it's working, and then when you're done, leave your source code, lab1.java, and the class file, lab1.class, in your lab1 directory for grading, and then I'll grade it at the due date then, and leave your README file there just like we did for your VI lab. Can you guys think of questions on anything we covered today? I might go ahead and stop the video then here, and we'll announce the due date then afterwards then, okay? Any questions? All right, you guys, let's stop here.